Hello my dear students, welcome to Dramatic Science. Myself Ayan. Today is the third lecture of heat transmission. Today we will discuss some four topics: conduction in varying thickness, Wiedemann-Franz law, convection, basically land and sea bridge, and fourth one is radiation, the basics of radiation with its properties, right? So let's start from the first point, conduction in a slab whose thickness is varying with respect to time. See, conduction through a slab of varying thickness. What will be its practical example? Like if you visit some cold region, the layer of a water body or a lake gets ice cold. The upper layer is filled with ice and at the down level there is water. So that is the process where these phenomena occur. What we need to calculate here, we need to calculate the time required for the heat to travel from that watery region to the air. Basically here the atmospheric air region is at minus temperature like this. So this one is the water body, this one is the ice slab, and upper is the air, that is at minus theta degree C, and water is 0 degree C. The width of the ice slab is x. The amount of heat is getting traveled from water to ice is dq, right? So heat conducted from water to air, in time dt. We are considering small amount of time for initial calculation. So dq will simply be Ka theta 1 minus theta 2. So here it is 0 minus theta, 0 minus of minus theta by x. X is the distance and dt is the time. So simply minus got plus. So Ka theta by x into dt. Now let us consider the latent heat of ice be L, its density be rho. And definitely one thing you must remember, that density of ice changes with the changes of temperature. So this density is at 0 degree C, right? So what do we know? dq equals to minus dm into L. How? Latent heat, the relation of latent heat and heat, that is q equals to ml. So here dq equals to dm into L. dm is the small mass of ice, and why minus? See, if the amount of heat increases, the amount of mass decreases in the ice. So that's why here is a minus sign. Put the value of dq, this one, and we will have the dm like this. Okay. Now let us consider the elementary width of this ice be dx and time is dt. So what we can say, dm equals to, dm means mass equals to volume into density. Here A is the cross sectional area and dx is the width of the ice. So area into width will be the volume. So A into dx equals to rho. Put dm, dm is this one, dm A dx into rho, A dx into rho. Then dx dt, dt goes this side, A rho comes this side, A gets cancelled out. So dx by dt equals to k theta lx into rho. So x dx equal to k theta rho L dt. Now we will integrate from initial slab width say x1 to final slab width say x2. So x1, x2, this is the slab width of this ice, right? So initial time is 0, final time is t, then we get this formula. If we consider the initial width of the ice as 0, that is x1 equals to 0 and x2 as x, say x1 equals to 0 and x2 as x, then we get the time, a simplified form, rho L x square 2k theta. This signifies that thus t proportional to x square. This is an important concept. So the time required will be proportional to the square of the width of the ice. Okay, so this is the conduction through a slab of varying thickness. Next, our second point, Wiedemann-Franz law. So Wiedemann and Franz's law. See, one thing you must know, that those materials who have good thermal conductivity may or may not conduct electricity so fluently. That means thermal conductivity and electrical conductivity are not similar properties. So Wiedemann and Franz derived an expression between those two conductivities. What they said, at a fixed temperature, the ratio of thermal conductivity, that is K, with that of electrical conductivity is constant. That is K by sigma is equals to constant, right? But Lorentz modified this form. According to Lorentz, he said Lorentz modification. Lorentz concluded that K by sigma, that is this ratio, is proportional to the temperature. That means we can say K by sigma T is a constant, and this constant is called Lorentz number, and definitely it has a certain value. Its value is, so this is the value of Lorentz number, 1.11 into 10 to the power minus 8 watt ohm Kelvin to the power minus 2. So this is Wiedemann-Franz law, the relation between thermal conductivity and electrical conductivity. Okay, next go to the third point, that is convection, the concept of land bridge and sea bridge. So now convection process. At the case of convection process, as I have written, molecules of gas or liquid travels from hotter to colder region. That means we can say at the case of convection process, molecular displacement is simply not equals to 0. Okay? And this process, this convection process is the main cause of creating convection current that we have learned in our geography classes. Convection current in ocean regions and all. Okay, now land bridge and sea bridge. So sea bridge and land bridge, here is a basic diagram to compare these two bridge, and trust me, I am not a good painter, so please try to understand. So sea bridge, at the case of daytime, the land region gets heated and the air corresponding to that land region, it becomes hot air, and hot air is lighter. So hot air from that land region travels in the upward direction, and cold air in the sea region comes to fulfill that vacancy, like this one. Cold air from this sea part is going to the region of land. So this air is coming from the sea, that's why it's called sea bridge. And at the case of land bridge, this is at night time. At the night time, land radiates heat so fast that it becomes cold. But at the case of water body, it convects, it transfers heat in a slower process. That's why the air nearby in the region of the sea is hot air, and hot air is lighter air that will travel in the upward direction. And to fulfill that empty space, cold air from land will come to that place. As the air is coming from the land side, it is called land bridge. So sea bridge occurs on the daytime and land bridge occurs on the night time. Okay, next our last topic, radiation. Simply basic, its properties and few words. So now the radiation process. Radiation process, that is, at the case of radiation process, no such medium is required for heat propagation, right? Like the heat energy coming from sun to earth, there is a huge vacuum. That's a process of radiational heat flow. Okay, here I will write some properties of radiation. Like number one, it travels in straight line. It travels with the velocity of light, that is c equals to 3 into 10 to the power 8 meter per second. It shows several phenomena like reflection, refraction, diffraction, interference, and so on. So these properties are also the properties of light, right? So from this thing we can conclude that light and radiated heat are simply same, right? So guys, that's all for now. I hope you have learned something new in this from this video, and if you have learned something, please give us a thumbs up, do comment, and please subscribe. You can share with your friends, right? See you in the next video. Be fit, be fine, and keep reading physics.